Okay. Are we live now?
Yes, you are live.
Okay, very good. I hope you all can see my screen and you're ready to start as well. So, yeah, today we are going to have two parts in this meeting. In the first part is like the lecture part, where we are going to cover what you see on the screen, SIMD processing and GPUs. The second part, we will stop the live streaming and then we will discuss the project proposals that we have for our students. So hopefully, I think I have around 70 slides or so. Hopefully this will be like 1 hour or so. And after that, we can go to the discussion of the projects. Okay, we are going to talk today about SIMD processing and GPUs. Welcome everyone to the second meeting of our P&S course on heterogeneous systems. Recall this picture from our first meeting where we show one possible heterogeneous computing system that contains CPU cores, GPU cores, reconfigurable fabric, and then different levels of the memory hierarchy, L1, L2 cache, last level cache, and also the main memory or the DRAM in this case, and different ways of accessing these different memories and communicating and synchronizing across the different devices that belong to the system. There may be CPU, GPU, and FPGA. There may be some neural network accelerators, for example, or there may be something else. So recall this slide also from our previous lecture. In this slide, we wanted to start with some classification of different types of systems or different types of heterogeneous devices that we can have. We talk or briefly introduce what's a SIMD execution model, SISD execution model, where a single instruction operates on a single data element. You can think about that sequential processor, a sequential CPU with a single core and a single thread of execution as a good example of SISD machine. Then we talk about SIMD, where a single instruction operates on multiple data elements, exploiting data parallelism. We are going to talk about this today. Then we also introduce the MISD machines, and multiple instructions operate on a single data element. And we talk about systolic arrays as the closest form to a MISD machine. And finally, MIMD machines where multiple instructions operate on multiple data elements. We have multiple threads of execution, multiple processes that can be doing something completely different and operating on different data elements. And this is what we typically execute on a multiprocessor or a multi-thread processor like current multi-core systems. We started in the previous meeting talking about SIMD processors, and we are going to go much deeper into them today, into the theoretical ideas of SIMD processors, because they are going to be the introduction to what is probably the most widely used accelerator these days, and probably the best representative of the heterogeneity of devices in computing systems, which are GPUs. And GPUs, as you will see, are more or less just a form of SIMD machines. SIMD machines exploit data parallelism, and I think it's good to start with data parallelism because, in my opinion, data parallelism is probably the most straightforward and simple way of exploiting the existing parallelism in programs. Why is that? Because in the end, data parallelism consists of having multiple pieces of data on top of which we want to operate, and we want to perform exactly the same operations on these pieces of data. The other day, I mentioned the example of image processing, where images, as you know, are composed by hundreds of thousands or even millions of pixels. And typically, the computation that we perform on each individual pixel is exactly the same. So here, it's an example that matches perfectly the example of, or the paradigm of single instruction, multiple data execution. Another example can be the dot product of two vectors, which is, by the way, used in matrix multiplication, as you know, and we will talk later today about matrix multiplication. In matrix multiplication, we compute each of the elements of the output matrix by performing the dot product of a row of matrix A and a column of matrix B, right? So there is a lot of parallelism, data parallelism there, so we can compute all the elements on the output matrix at the same time by having different processing elements, like, or different threads of execution, computing the different dot products that we need to obtain the final elements of the output matrix. There is a contrast here with data flow. In data flow, the concurrency, the parallelism, arises from executing different operations in parallel. It's more like a form of task level parallelism, where we identify different operations that are independent of each other, and they can be executed in parallel on different machines or different devices. And it also contrasts with thread level or thread or control parallelism, where concurrency arises from executing different threads of control in parallel, something similar to what we can have in a multi-core processor, where we execute, for example, different programs or different threads of a program doing completely different things on different cores. In SIMD, the parallelism comes from the ability of performing the same operation on different data. In some way, this data level parallelism is a form of instruction level parallelism, right? The thing is, because we can have multiple instructions executing in parallel. The thing in SIMD is that all these instructions are one single instruction being executed on multiple pieces of data. So this is data parallelism, and this is SIMD processing. Single instruction operates on multiple data elements. The way that we perform this parallelization can be in two different ways. That can be like solely implemented on a SIMD processor, or they can even coexist. One of them is in time, and the other one is in space. In both cases, we have multiple processing elements that we call processing elements or execution units. We will later call them SIMD lanes as well. And these processing elements might be used in time or might be used in space, as I said. So this time-space duality gives us the first classification of SIMD processors, where we distinguish between array processors and vector processors. We are going to see a very clear example in the next slide, but let me first define what's an array processor. It's a processor where one instruction operates on multiple data elements at the same time using different spaces. Okay, so same time, different spaces, while in a vector processor, the instruction operates on multiple data elements in consecutive time steps using the same space. Let's take a look at what this means. Here on the left, you have an array processor. You can see that it consists of 4 processing elements. They are the same type of processing element, P0, P1, P2, and P3. And here on the right, you have a vector processor. You also have 4 processing elements, but these 4 processing elements are kind of specialized, right? So one of them is designed to execute load instructions, the other one to execute additions, this one multiplications, and this one store instructions. And now what we are going to do is executing on these 2 types of processors, this instruction stream that we have on the left. This instruction stream is the program that we are going to execute in these 2 SIMD processors. And as you can see, it's like our first vector processing program, or first SIMD processing program that consists of only 4 vector instructions or SIMD instructions. In the first one, we load a number of elements from one array in memory, which is A, into some registers, and these registers are scalar registers that all together form what we call a vector register. Then we increase the value in each of the individual elements of the vector register by using this vector add instruction. Then we perform this multiplication. We multiply by 2 each of the individual values that that are stored in the vector register, and then finally we store to the same place, to the same array A. How is this executed on an array processor? So because we have 4 values that we are going to compute, that we are going to process from array A, we have 4 processing elements, we can load the 4 values at the same time. So each of the processing elements takes care of each of the 4 individual loads. then we perform the addition, then the multiplication, and then the store operation, always using the same processing element. However, in the case of the vector processor, what we do is starting with the load. Because we have one single load unit, we can only perform one load at a time. And in the next cycle, we can perform the load of the next element of array A, right? And also at that time, we can start performing the addition for the first element that we read in this cycle, right? So observe how we create a pipeline of instructions here that are being executed. And this way, on the array processor, we have the same operation at the same time, while in the vector processor, at the same time, we have different operations because the processing elements perform different operations. And so here you can see the duality of time and space, right? And here in the array processor, different operations are in the same space because this processing element can execute either a load, an add, a mul, or a store. While here in the same processing element, we always execute the same instruction. In this case, all of them are add operations. Okay, so now we have the first classification of SIMD processors, vector and array processors. We will see that there are a lot of similarities between them, and also they both exist in some way in current graphics processing units, as we will see. Let's talk a little bit more about SIMD processor, and in particular in this slide, we focus on vector processing, vector processors. We usually, as I said in the beginning, we are going to use SIMD processors where we can exploit data parallelism. A good example is a simple program like this one, where we have a for loop with 50 iterations. What we do is go into memory to read one element from array A, or one element from array B. We add them, we divide by 2, and then we store in the corresponding element in array C. The good thing here is that there is the data parallelism, and we could execute these 50 iterations of the loop at the same time if we had 50 processing elements, right? So basic requirements are for this to happen. Basic requirements is that we need to have vector registers where we store the elements that we read from memory, from array A, from array B, and where we store the output results that we will later store in array C. We need to define as well what's the length of the vector processing that we want to perform. In this case, that length is determined by the number of iterations of the for loop. As you can see, is 50. So in principle, we could say, okay, let's define our vector length as 50. And now let's execute the 50 iterations at the same time, assuming that we have 50 execution units or 50 processing elements, right? And also, one important thing that we will discuss later more in detail is that we need to handle as well the access to memory. We need to read from A, we need to read from B, and then we need to store in C, right? And the way of accessing memory is determined by a vector register, by a register that is called vector stride register that defines the stride, which is the distance between consecutive elements that are going to be accessed. So not consecutive elements, but the distance between the elements that consecutive lanes of the vector unit or the SIMD unit are going to access. Then in the simplest example, we will consider that this stride is 1, and 1 means that the distance between one element and the next element that is going to be operated on by the vector instruction or by the vector processor resides in the next position in memory. And that's actually what we can see here, where we are computing element 0, element 1, element 2, element 3, and so on, right? In some other cases, we will see that this stride might be longer. For example, 2, if we are only operating on the even number or the odd numbered elements of these arrays. Okay, guys, feel free to stop me if you have any questions at any time. I was talking about the strides, and here you can see your first example of different strides in matrix multiplication. So in matrix multiplication, as you know, what we do is computing an output matrix C it's the multiplication of two input matrices A and B. In this case, we consider one matrix A of dimensions 4 times 6 and matrix B is dimensions 6 times 10, and finally we will obtain an output matrix which is C of size 4 times 10. It's a very toy example, as you can see, but I think that it's quite illustrative. So when we want to compute each of the elements of the matrix C, what we have to do is performing these dot products that I mentioned before. In this case, if we compute element 0, 0 in matrix C, we will need to read this whole row first, the row 0, the first row in matrix A, and this first column of matrix B, and then perform the row, the dot product, right? So there are different, so we have to access these two arrays A and B, or these two matrices A and B, or the vectors that we extract, the row from A and the column from B. We have to access them in a different way. We access them with different strides. In the case of matrix A, it's very simple because these matrices are stored in memory in a linear manner. So consecutive elements in the same row are mapped to consecutive memory locations in memory. So when it comes to reading these 6 elements from matrix A, we read 6 consecutive memory locations. So in this case, the stride is 1. When we have to, the number that we need to put in our vector stride register is 1. However, when we want to access matrix B, observe that these elements, these consecutive elements in the same column, in reality are mapped at a certain distance, which is the stride in the linear memory, right? So in this case, the stride is 10, and in this case, in the vector stride register, we'll have to write 10 because that's the stride that we use to access matrix B. Okay, we know already that a vector instruction or a SIMD instruction performs an operation, a single operation on multiple data elements. The way that this instruction is executed depends on whether we talk on an array processor or a vector processor. If it's a vector processor, it will be in consecutive cycles, as we saw before. This it's ideal for the execution because we can achieve a lot of performance by exploiting the data parallelism when this data parallelism is completely regular, which means that we really are going to execute exactly the same sequence of instructions on different data elements. But sometimes our program or our algorithm might be more complex and might require some control for divergence or some more fancier data accesses, right? For example, indirect memory accesses, which are usually more complex to execute and to design as well when we are writing the code. So if we don't have those restrictions, then everything is perfect. We will achieve very good performance by exploiting the regular data parallelism. But if that's not the case, then programming becomes much more complicated. And recall this slide that I showed you the other day from Fisher in the year 1983. He already said that programming SIMD processors was hard to do and just as hard to change. This slide is important because it clearly shows the disadvantage, the main disadvantage of SIMD processors, and also is very good to motivate what GPUs have enabled in terms of being much more friendly to the programmers, but is still achieving an amazing performance and amazing speed ups when we have some data parallelism. So that's what we will see in a few slides. Okay, we talk about vector data registers is where we are going to store the values that we read from memory and where we are going to store or intermediate results that we will later write onto the output arrays in memory. We also have some control registers, the vector length, the vector stride, and the vector mask. We already know that the vector length is the number of elements that we want to operate on at the same time. For now, we consider this vector length kind of programmable, right? We can write the number that we want in principle in this vector length. We will later see that many SIMD architectures, including GPUs, fix this vector length to a certain number. It's actually typically 32 in Nvidia GPUs, for example. We also have the vector stride, that we need to use to access memory, and we also have a vector mask register. The way that we are going to use or the purpose for which we are going to use this vector mask register is to execute, for example, if-else statements or conditional branches. We will see how in a few slides. But first, let's recap a little bit on how we access memory. Recall, when we want to perform some SIMD computation, some SIMD processing, we need to use vector instructions. These vector instructions operate on elements, on values that are stored in vector registers. But before we have these values in the vector registers, we need to access them from memory, right? And to do so, we need one address in memory, which is the base address of the array that we are accessing, for example, array A. And then we also need a stride, which is the distance between consecutive accesses to memory, right? And the thing is, if we have to perform 50 accesses in parallel, for example, if our vector length is 50, how do we need to design our memory to be able to obtain all 50 values at the same time, or almost at the same time, such that we don't need to serialize all the accesses? Like, okay, let's access element 0, here is element 0, now element 1, here is element 1, now element 2, here's element 2, and so on, right? We want to avoid that. We want to be much faster. And the way of doing this is by partitioning the memory, dividing it into what we call multiple memory banks. Essentially, the idea is that instead of having a single block of memory, a monolithic memory that needs to be accessed sequentially or serially, we can perform multiple accesses in parallel, right? So we divide the memory in this example into 16 different banks, and we have one common data bus and one common address bus. When we want to access element A0, what we will do is writing the address of this element 0 in this memory address register. Then we start the access to the bank 0. That will take a few cycles, let's say 11 cycles, for example. And after 11 cycles, we will have the value that we needed, we wanted to fetch from memory. We will have it here in this memory data register, right? Good thing is that I said 11 cycles. During these 11 cycles, we can continue writing addresses in these different MIRs, right? And this means, and we can do it in one cycle. We write one new address in this MIR, and then this MIR, and this the next MIR in the next cycle. So we are taking advantage of the 11 cycles that we need to access bank 0 to start accessing bank 1 for element A1, bank 2 for element A2, and so on, right? And then after 11 cycles, we start reading the elements. We start gathering all the elements one by one using this data bus from this MDR, this MDR, this MDR, and so on, right? So this is how we access memory for both reading and writing. Let's go back to the example of the vectorizable loop of this for loop where we perform this addition, then divide by 2, and then we write to the output C array. If we want to, so this is our sequential code, this is kind of C code, right? And now we want to write our vectorized code. In our vectorized code, the first thing to do is defining what's the vector length, in this case is 50, defining what's the stride, in this case is 1. Note that we are writing 50 in vector length, in the vector length register. We are writing 1 in the vector stride register, and then we start with the execution of the vector instructions. This is vector load for the elements, the 50 elements of array A. This is another vector load for array B. Here we have the vector addition. This is a vector shift right. We shift one position to the 1 bit to the right, which is essentially the same as dividing by 2, and finally we store with this vector store. And here on the right, you can see the latency of these individual instructions. These move I and move I are not vector instructions, so they just take a single cycle, and then we access memory with this vector load, and then with this other vector load. Recall that in our example, we were considering that the access to one bank was 11 cycles, and then after the first 11 cycles, we start gathering or fetching one element from each of the other banks, right? So in total, the execution of this vector load is going to take 11 plus vector length minus 1, 11 plus 49 in our example. And in a similar way, we are also going to use, recall, vector processors where we exploit the parallelism in time. So we start executing cycle after cycle this addition for the 50 elements that we have in these vector registers, and this shift right, and then the store operation. And this in total is 7 dynamic instructions, which, by the way, it's we are reducing a lot the number of instructions that we have to write, and also the number of instructions, not that we have to write, because this is quite compact because the loop is not unrolled, but the number of dynamic instructions, the number of total number of instructions that are going to be executed by the hardware here in this sequential code is much larger than the number of dynamic instructions that we have when executing the vectorized loop. Okay, so for now, we are going to assume no chaining. No chaining means that there is no data forwarding across processing elements. You will see what chaining is in the next slide, actually. So we assume that the entire vector register is ready when before starting the execution of the next instruction. Another assumption here is that we only have a one memory port per memory bank, and also one single address generator. In our example, we are going to consider that we have 16 memory banks. That's what we were considering in the previous figure, and this is how the instructions are going to be executed, right? So recall that it's this code here. The way that we execute this code on our SIMD processor or our vector processor is by first move 50 to the vector length, move 1 to the vector stride, and then we start the execution of the vector load instruction, where we read from A, then the vector load to read from B, vector add, shift right, and store, right? And then in the execution of these individual instructions, what we have is first the whole latency of the first operation, and then after one cycle, we start receiving the result for the next lanes of the vector, or the next elements in the vector. In total, this execution takes 285 cycles, which is already much shorter than what this takes to execute in a sequential processor, as you can calculate yourself. One way of optimizing this execution is by using vector chaining. In vector chaining, what we essentially do is start computing as soon as we can, right? You remember that this vector add, what it's doing is adding individual elements coming from A and B. So we can start the execution of the additions in the vector processor, in the vector processing elements, as soon as two values, one from A and one from B, are ready. So A0 and B0 are both ready here at this point, so we can start the execution of this addition. And as soon as we compute element 0 of this vector register B2, we can start the execution of the next instruction, which is this shift right that takes one cycle, and then we have to wait 49 more cycles to complete the execution for the 50 elements of the vector, right? We can reduce the execution time quite significantly as well here by using this chaining technique. But still, notice that it is possible to improve our hardware even more and obtain even more performance. For example, these two instructions, this vector load and this vector load, in reality are completely independent, so they could be executed in parallel. The only reason why they are not being executed in parallel in this example is because we are assuming one single memory port per bank. And what this means is that we have to first use this bank to access the corresponding elements from array A in bank 0, and then the elements from array B in bank 0 or in bank 1 or in bank 2. Solution, what we can do is using two ports per bank. And if we do that, we would be able to exploit more memory bandwidth. We are able to read more data from memory in the same cycle, in the same amount of cycles, and we can parallelize the loads, as you can see here in this example, in this part of the figure, and even can later parallelize some load operations with the final store operation here. So in the end, we reduce the total number of cycles a lot. We have 19 times performance improvement when compared to a sequential machine. Okay, so now more or less we know how the vector instructions are executed on a vector processor. I said in the beginning, vector processors and array processors, SIMD processors in general, are very good when it comes to exploiting very regular data level parallelism, but we also need them to give us the possibility of computing something a little bit more complex, a little bit more irregular. For example, there are conditional operations in this loop that we have here. Again, we have n iterations. So in principle, we would define our vector length equal to n for this example. But then inside the loop body, what we have is an if statement. We are comparing each of the elements of A with 0. And then depending on whether it's 0 or not, we perform this computation or not. So if we want to perform these conditional operations, we need to use the vector mask register that we presented very briefly before. And this is something that in principle, the programmer has to do by herself or himself. It's generating the mask, because this mask, which in the end is just kind of a bitmap where each individual bit represents each of the lanes of the vector unit. This mask, this bit, defines whether one particular operation, the next operations, are going to be executed or not. So, for example, in the for loop that we have here, we need to compare AI to 0 and then execute this multiplication or not. So to do that, what first we do is load, using a vector load, the element of A into vector 0, and then we compare each of the values in vector register 0 to 0 to generate this mask. If this predicate is true, then the corresponding bit in the vector mask is 1. If it's not true, then the corresponding bit will be 0. And then for those lanes where the bit mask, the mask bit is 1, we will execute this multiplication and this store operation. And this is what we call predicated execution. Bekhtat, there is a question from you. Do you want to clarify what the question is?
No, this is a question in the YouTube, sorry.
Is there a way to overlap the vector loading with only one port? So if we have a single port per memory bank, we can only have one single load or one single store per memory bank. So we are exploiting some parallelism by using multiple banks, that's for sure. We may have, in some examples, in some systems, we may have multiple load ports and multiple write ports as well. So in some cases, we can have, on the same bank, we can be reading or writing at the same time on the same bank. But this, if we have a single port per bank, I don't think that we can perform two loads from the same bank. Thank you, Bekhtat. Okay, so I was talking about mask operations. This is what we call the predicated execution. The execution is predicated on a mask bit. If the bit is 1, then we execute the subsequent instructions for that particular data elements. If not, we don't execute. This is the predicated execution. Again, observe that if you are the programmer and have to write these, it will be really, let's say, inconvenient, right? So even more if you have more nested loops and nested if-else statements that are going to make much more complex to handle the vector mask. Okay, here we have another example with masking. In this case, it's a little bit more complete because we have the if and the else statement. But again, we operate the same way. In this case, we have to compare the element of A and the element of B. If AI is greater or equal than BI, the mask will be 1, the mask bit will be 1, if not, it will be 0. So we first execute this part, then we complement the mask. So we flip all the bit of the masks and we execute the else statement. Okay, a few more issues, a few more complexities when programming SIMD processors. We have to take into account the stride. I mentioned how to use the stride before. We need the base address, then we need to stride the stride to calculate the addresses, the exact addresses from where we want to read or where we want to write. But we also have to be careful about how we use this stride. Why is that? Because in the end, we have a fixed number of banks, right? And in this number of banks is relatively small. In our previous example, it was 16. In current GPUs, I think in Nvidia GPUs, if I'm not wrong, it's 32, but it's a relatively small number. Now, if we are accessing consecutive elements of the matrix or the array, these elements, consecutive elements, are going to be mapped onto different consecutive banks, right? And so we can perform the access to A0 and A1 and A2 at the same time, and we can access as many banks as we have, 16 accesses at the same time. But what happens if we have a larger stride? Okay, if we have a stride equal to 3, there is no problem, right? We are going to be accessing element 0, element 2, element 5, and so on, and there won't be any conflict. We can still perform all the accesses in parallel. But if we have a number, a stride equal to 2, for example, we would be accessing element 0, 2, 4, 6, 8, and so on. And then at some point, recall 16 banks, which means that element 16 is in bank 0. The problem is that we try to issue and we try to access at the same time 2 elements that reside in the same bank. And because this happens, we cannot access them at the same time if we don't have 2 ports at least, right? 2 write ports, 2 read or load ports at least. And this is quite a frequent problem in many different examples where, for example, we need to access a 2-dimensional organization, data organization, like, as a matrix. Like we saw the example of the matrix multiplication, and these elements of the same column are at a certain distance, are at a stride 10. This 10 is not, so it's not prime relative to 16, for example. So this means that we will have bank conflicts at some point. If you calculate the destination, I mean, you calculate the bank that we need to access to for elements 0, 10, 20, and so on, you will see that many of these accesses are going to fall into the same bank. And this is what we call a bank conflict. There are ways of minimizing these bank conflicts. Don't worry for now. We are going to very briefly mention some ways of minimizing bank conflicts, but we will talk in later lectures again about bank conflicts and how to avoid them when programming a GPU. Let me very briefly remind you what the bank conflict was. I gave you the example before of accessing with a stride equal to. If we access with a stride equal to, we would probably be accessing element A0 here, element A2 here, element A4 here, and so on. And then, as I said, element A16 is again in this bank 0. And if it's in bank 0 and we want to access A0 and A16 at the same time, we either have 2 load ports or we will have to serialize the access. Of course, having more ports is always a possibility, but also is more expensive from the hardware point of view. And this is actually one of the potential, let's say, most naive solutions to minimizing the bank conflict, same as we can have more banks, or we can, for example, try to have a better data layout that maps the elements in a different way, not in a consecutive manner, as we are assuming so far. But these may not always be possible, right? And also another way is like better mapping of address to banks. There are, like, for example, randomized mapping. We may come up with some expression using, for example, XOR operations to calculate the destination bank of one particular address. And this way, there are many good examples, like, for example, this paper from Bob Rao in ISCA 1991 that explain and propose techniques to randomizing these accesses to the banks, and this way reducing the number of bank conflicts. But as I said, we will talk again more when we go to our GPU programming lectures. Recall that the other day we already talked about SIMD operations. We talked about one case of real world SIMD processor, let's say, which are the ISA, the SIMD ISA extensions. We saw this example where we do some image processing using MMX instructions. In this case, is overlaying the human image on the background image. We saw how this computation can be performed by using these pack instructions, which are the vector instructions or SIMD instructions in this MMX instruction set. If you want to learn more about SIMD processing, I would definitely recommend you this lecture from Professor Mutlu from our bachelor's course, DDCA, Digital Design and Computer Architecture, where you can see a much more detailed description of all these concepts that I already explained. What is the possible maximum size of a bank? I mean, if that's a question from YouTube. So if you mean the capacity of a bank, that is defined by the total size of memory, right? You may have 1 megabyte size of memory or 256 kilobytes. Let me give you the example of Nvidia GPUs, typical values for the shared memory, which is a banked or interleaved memory, similar to this one that we are describing. There, the total size is typically 64 kilobytes. So if we have 32 banks, for example, this means that the size of each bank is 2 kilobytes. And there are some proposals, for example, to reconfigure the number of banks, right? But these are not, I mean, of course, if you want to reconfigure the number of banks depending on or the characteristics of your program, and this way reduce the bank conflicts for that particular program, that will require some extra hardware. But there are many proposals about this, and we will mention some of them in future lectures. I have one more question in the chat. What's the difference between more ports and more banks? Are there any differences in performance? Well, that will depend, right? I will let you think about what could be more beneficial in terms of performance for a particular program. But in the end, the important thing here, rather than thinking whether something is better or worse in terms of performance, is to really understand what's the difference between one thing and the other thing. So when we talk about banks, what we mean is the different parts that compose the memory. We take the whole memory, we divide it into multiple parts, and this multiple number is the number of banks. So we divide the memory, in this example, 16 banks. Then what's the port? You can assume that the port is these two registers here plus some add unit that obtains the address that we will write here from a base address, the start address, the pointer that points to a matrix A, for example, or array A, and the stride. By using the stride and using the base address, we can obtain the specific addresses of the elements of A that we want to access in the different banks, right? So this is one port, this is another port, two different banks, two different ports. Instead, we could have duplicated MDR and duplicated MIR for each bank. If we have two MIRs, this means that we can access two addresses at the same time from this bank. Of course, this will come with some circuitry that you need to design to do that, right? But in theory or in principle, it's possible to have that, to have multiple banks, multiple ports to different banks. And after that, as I said, you can, after understanding perfectly well what's the concept of a bank and the concept of a port, you can think about what would be more beneficial for a specific problem, the specific program that you have in mind or algorithm. Okay, we already went over these slides, and I was recommending you these. Thank you very much for the questions, by the way. Please don't stop asking. I don't care if this lecture takes for longer than expected, as long as you are asking good questions and I'm able to answer them. So I was recommending you this lecture on SIMD processing. If you want to go deeper into the understanding, Professor Mutlu, for example, will also talks in this lecture about Cray systems, which were the first big machines that they started to, well, not the first, but were very powerful machines, powerful supercomputers using vector processing units. And at ETH, we have one nice one from the 80s that you can visit someday if you are around the CAB building. Okay, now we are done with SIMD processors. As you will see, they are like the, so in some way what I did was explaining the basics of GPUs, which is what comes now. It's this device that we have here in the middle of our heterogeneous computing system, and here you have the layout. You already saw this block diagram of the most powerful GPU from Nvidia, released in year 2020. This is the A100. It's a kind of a amazing thing, right? With hundreds of cores, 128 GPU cores, each of them composed by many processing elements or SIMD lanes, as you will see, and also very large L2 cache of 40 megabytes. And here you can see also the memory controllers to access the HBM2 stacks, high bandwidth memory to at least be able to feed as many data as possible from memory to all these compute elements that we have in the screen. But this thing that looks like amazing, right, and super complex is in reality as simple as these two SIMD processors that we have, the array processor and the vector processor. And recall the differences. In the array processor, we have the same operation at the same time. We have different operations at the same space. In a vector processor, we have different operations or different instructions at the same time, but we have the same operation at the same space. And this is exactly the same. And actually, these two forms of SIMD processors is what we have if we take a closer look at one of the cores of the A100 core. So recall, in the array processor, we have many processing elements that are exactly the same, or we have some processing elements that are exactly the same. In the vector processor, we have different processing elements that are specialized, right? And this is what we have here. If you look at these int32 processing elements that we have, they are exactly the same, and they are int32, which means that they are arithmetic logic units to execute different instructions, different operations, as long as they operate on int32, 32-bit integers. But here we also have floating point 32, and here we have floating point 64 bits, and here we have some load and store units, and here we have SFU that are special function units, also some sort of processing elements, and also these tensor cores that I mentioned briefly in our previous lecture and are specialized for AI and machine learning workloads. We will talk a little bit more in detail about these tensor cores at the very end of this lecture. But important thing at this point is that observe that here we have the time duality, the time-space duality in the same place, right? We have different types of processing elements, and then we have replicated processing elements to execute multiple, so the same instruction on multiple data elements at the same time. So in the end, what's this? It's a SIMD processor, right? And there is one more thing. I was just mentioning a few slides ago the interleaved or banked memories, and I mentioned the shared memory. This shared memory is a scratchpad memory space. Scratchpad meaning kind of a software cache, then on-chip cache, because it's inside the GPU core, that where we can store operands, input and output operands that we read or write to memory. And this shared memory in the end is a banked memory, as I said, and I already mentioned that it's typically 32 banks, not 16 as this example. But again, the idea of SIMD processors, so GPUs are essentially SIMD processors. It's what I want to convey. GPUs are SIMD engines or SIMD processors underneath. The instruction pipeline operates like a SIMD pipeline. We already know how a SIMD pipeline works, and we are going to see much more clear how it works inside the GPU. However, the key difference, and this is where we are going to spend the next few slides, is that programming is not done by using SIMD instructions or vector instructions that like this vector load or vector add that we just discussed. Here, we are going to use threads. We are going to program these GPUs as if they were a multi-core processor, more or less. But to understand this, we will go and we will discuss some parallelizable code as this vector loop with the vector addition that we have seen before. But first, we want to really distinguish what's the difference between the programming model, which is a software concept, and the execution model, which is a hardware concept. And I'm going to give you several examples of these. The programming model refers to how the programmer expresses the code. And there are many different ways of doing this. I know that you guys are familiar with C and C++ programming. Maybe you also have some experience with parallel programming, like maybe using Java threads, or maybe using OpenMP or P threads, or maybe using CUDA or OpenCL. There are different ways of expressing the program, right? We can express more parallelism or less parallelism, for example, and we can do it in different ways. We can express the data level parallelism or the data flow parallelism or concurrency, as we mentioned before. But then the execution model refers to how the hardware executes the code underneath, and this might change as well. So if you think about that C program, a sequential program, you could run it on an in-order processor, something as simple as a MIPS processor, for example, that we typically study in the digital design and computer architecture course, or something more complex like a out-of-order processor. So one thing is how we write the programs, and another thing is how the hardware executes that program, that code. So the execution model can be very different from the programming model. For example, we can write a sequential code and execute it on an out-of-order processor, as I mentioned, or we can write a multi-threaded core, what we call the single program, multiple data programming model, which is the one that applies to GPUs, and execute it on a SIMD processor. So a GPU is a SIMD processor underneath. What we change is the way that we program it. We don't use vector instructions, we use threads. But let's take a closer look at the example. This is our parallelizable or vectorizable code with this for loop, where we have completely independent iterations of each other. We can execute all these iterations in parallel, and we can write this as a sequential program, right? We can use a programming model that is simply sequential programming, same as the thing that we wrote here using C language. And then we can execute these in different ways. We can execute it in an in-order processor, where we execute instruction by instruction, first this load, then this load, then this add, then this store, then this load, and so on. Or we can try to exploit the parallelism that exists here. For example, this load instruction is completely independent of this one, or this one is completely independent of this one. So I could execute them together if they are in the same, for example, vector load instruction. And then I can also write a multi-threaded code where different threads execute different iterations, like this one to thread 0, this one executed by thread 1 in a multi-core. This could be executed on core 0, this on core 1, and so on. So let's first take a look at the simplest case, right? The sequential program in the SISD paradigm. We write the sequential code, and then we can execute this either on an in-order pipeline processor or an out-of-order processor, or even a superscalar or very long instruction word processor. The only difference between all of these is in the execution model, where we have the ability, as the more complex the processor is and the more features the processor has, it has the ability to extract parallelism that naturally resides in the programs, right? So here, this sequential code that is going to be executed in several different iterations, as you can see here on this part of the slide, there is inherent parallelism. The out-of-order processor detects that, for example, these two loads are independent of each other, so it can issue these loads to memory almost at the same time, because one doesn't have to wait for the other one, right? Later, it will see that this add is dependent on these two. So obviously you cannot start the execution of this one until these two are done, right? Unless you do some sort of speculative execution that you may need to roll out later. But yeah, so these are like different ways, different execution models using the same programming model. The second possibility is to exploit the inherent data level parallelism that we have. And we realize that each iteration is independent. Because they are independent, they can be executed in parallel. So we can create vector instructions, as you know. This is vector load A, vector load B, this is vector add, and vector store, right? So this is how we know that we can do in a SIMD machine, in a SIMD processor. And then the third programming model is the multi-threaded. In the multi-threaded programming model, for example, if you guys are familiar with OpenMP, you know that something that we can do as simple as writing before this for loop, something like pragma parallel. And this means that the compiler is going to create different threads of execution, and the hardware is going to execute these different threads probably on different cores of a multi-core machine, and each of them is going to be taking care of different iterations of this for loop. So this is how we would write code in a multi-threaded machine. Again, the realization is the same as in the vector processors or in the SIMD processors, is that each iteration is independent, but now the difference is that we are not creating vector instructions here. We are creating different threads of execution. And this is what typically, I gave you the example of multi-cores, which are probably the best example these days about that for a MIMD machine. This particular model, this particular programming model can also be called single program multiple data, because notice that we have a single program, each individual thread executes this program, but each individual thread is operating on different data elements, right? And this is what is called, as I said, SPMD, also called SIMT, because SIMT comes from SIMD, single instruction multiple thread, comes from single instruction multiple data, because they are essentially the same. So a GPU is a SIMD or SIMD machine. The only difference with a SIMD machine is that it doesn't execute SIMD instructions, it's programmed using threads, and then the hardware itself will be able to create the vectors in a transparent way. The programmer writes code for individual threads, and later, as we will see, or we are going to see in the next slides, the hardware creates these warps, so-called warps or waveforms, depending on the GPU vendor, and executes them together onto the hardware as if they were vector instructions. They were, the different threads were different lanes of the same vector instruction. So a SIMD, a warp is essentially a SIMD operation formed by hardware, or in some, we can better say, a warp is a set of threads that execute the same instruction. For each warp, we have a sequence of instructions that are going to be executed one after the other. For example, this instruction here, observe that is not a vector instruction. This is a warp instruction that resides at PCX. So this is instruction X for warp 0, and this is instruction X plus 1 for warp 0, X plus 2, X plus 3. Okay, let's go into the details. Graphics processing unit are SIMD not exposed to programming, and this is what we call SIMD. So what's the difference, again, between SIMD and SIMD? Let's recap on this. In SIMD, we have a single instruction stream or multiple SIMD instructions. We use vector instructions or we use SIMD instructions. In SIMD, we have multiple instruction streams, multiple threads, executing scalar instructions, and then the hardware groups these threads and creates the warps. That will be kind of the vector instructions that are executed on the SIMD engine. So this programming model has, or this execution model has two main advantages. The first one is that each thread can be treated separately. So you can write a CUDA program where each individual thread 0, thread 1, thread 2, thread 3, and so on, they do completely different things. And then the hardware will put these threads together as much as possible and execute them together in order to exploit the SIMD execution units. And also one other advantage is that the threads can be grouped flexibly, and this is going to allow the conditional execution, as we will see in later slides. But let's first talk about the first advantage. Each thread can be treated separately. Recall the idea of the, well, this vectorizable loop that we have just analyzed. Recall that in a GPU, what we do is writing this as using the SPMD programming model, single program, multiple data. We create multiple threads, and each of the individual threads is going to execute one of the iterations of the loop. We create our program. We will see very soon how we write our program, then we launch this program onto the GPU, and then the hardware starts creating these warps that are executed on the SIMD engine, right? And each of the warps behaves kind of a vector thread or something like that, and has to execute a sequence of instructions. Yeah, so I was going to tell you, how do the GPUs internally, the hardware group creates these warps. Typically, we have the number of threads. These threads have each of them an ID, thread 0, thread 1, thread 2, thread 3, and so on. Maybe we are using millions of threads in our program, and then the hardware takes 32 consecutive of these threads, typically 32 in Nvidia architectures. If I recall correctly, AMD architectures were using a vector length of 64. So it would be either 32 or 64 consecutive threads form the first warp, the next 32 or 64 threads, the next warp, then the next 32 or 64 threads, the next warp 2, for example. So this is how the threads are usually, how the warps are usually created by the hardware. And then for each of these warps, we have a sequence of instructions that we have to execute. Recall that we said, okay, this is instruction X for warp 0, instruction X plus 1, instruction X plus 2, and so on. So each of the warps has its own program counter. And then when it comes to execute the different warps onto the available hardware, onto the SIMD pipeline, onto the SIMD execution units, we have a so-called warp scheduler that checks what are the instructions from different warps that are available for the execution, because they are not waiting for results from previous instructions to be written into the output register. So they are eligible for execution. You can take the instruction, you can launch instruction. For example, here in the screen, we have instruction X for warp 0, and then instruction X for warp 1. Notice that these two are completely independent, because warp 0 and warp 1 have completely independent threads. So they can be, these instructions can be issued one after the other, cycle after cycle, right? And after instruction X for warp 1, we have, for example, instruction X plus 2 for warp 20, and so on, right? And what we are doing here is launching onto the SIMD pipeline different instructions coming from different warps, right? So what we are doing is kind of interleaving the execution of instructions coming from different warps. And this architecture and this paradigm is what we call the fine-grained multi-threading of warps. And fine-grained multi-threading is like the other important computing paradigm that is part of GPUs. So GPUs are in some way part SIMD processors and part fine-grained multi-threaded processors, because this idea of fine-grained multi-threaded wasn't invented for GPUs. It is much older, and actually I have a couple of slides here to remind you what fine-grained multi-threading execution is. In fine-grained multi-threading, we have multiple hardware contexts, we have multiple thread contexts. When we talk about a context, we mean a PC, a program counter, and a number of registers to store the operands, input and output operands of our instructions. And in each cycle, the fetch engine, which is the warp scheduler in the case of the GPUs, fetches a new instruction from a different thread. And then it launches it onto the pipeline for the execution. In the case of the GPUs, these threads are not individual threads, they are warps. And this is why sometimes, and actually in later slides, you will see that we call the warps thread warp, because they behave as a thread in a fine-grained multi-threading machine, but it's not a single thread, it's like several threads that compose the warp. The key idea, as I explained before, the key idea in fine-grained multi-threading is to switch to another thread every cycle such that no two instructions from a thread are in the pipeline concurrently. And this way, we avoid completely the dependency between consecutive instructions or neighboring instructions in the same program for the same thread or for the same warp on the GPU. And this is the key idea of fine-grained multi-threading. And if you think about how can be useful this key idea is by thinking about something that, I mean, it's like the main purpose of these fine-grained multi-thread processors, which is, by the way, one of the key strengths of the GPUs is the fact that when you start the execution of one instruction, if this instruction is going to take too long, you don't have to worry, because you have many more warps, you have many more threads that are independent of this long latency instruction, and you can continue executing them onto the pipeline. And typical example of long latency operations are memory accesses, right? Because when you go to the off-chip memory, even if it's HBM2, which provides very high bandwidth, the latency, the number of cycles that you need for the access is still very long. Recall the example of memory banking, I was talking about the latency of 11 cycles. Usually it's longer than that. Usually accessing the off-chip DRAM in current GPUs takes several hundred cycles, right? So the way that GPUs hide this long latency for the access to the DRAM is by executing other instructions from other warps onto the pipeline. And this way we have this latency hiding mechanism. If you want to learn more about fine-grained multi-threading, I would also recommend you this lecture 14 taught by Professor Mudlu in the past spring semester. And here you have two more links to two more lectures on fine-grained multi-threading. But yeah, I already explained you how we use fine-grained multi-threading and how we use it using warps on the GPU. But this is more or less a summary slide of what I just explained. We have these thread warps, which are the warps inside the GPU core, and each of them has it's composed by a number of threads, and all of them have a common PC. And different warps have different PCs. And actually, you can see it even more clear in this picture, which is kind of a high-level view of a whole GPU with the different GPU cores or shader cores. Here you have the interconnection network that gives access to these shader or GPU cores to the memory controllers and the external off-chip memory. But then if you check the internals of each of the GPUs, of the GPU cores, you see this thread context or warp context, which is the PC, the program counter for all the different warps that execute on this SIMD execution engine, and also the mask, because recall, these are SIMD processors. Because they are SIMD processors, we also need mask registers. The good thing in GPUs, as we will see soon, is that this is completely handled by the compiler and by the hardware, and the programmer doesn't need to deal with this mask, or doesn't need to deal directly with this mask. Of course, if you know that the mask exists and what are the restrictions that it imposes, you will be able to write more efficient and better performance code. And again, the idea of fine-grained multi-threading applied to warps with the aim of hiding long latency operations, right? So here you have another view of the SIMD engine, which is each of the GPU cores. Here we have the instructions from different warps available for scheduling. As they are ready for execution, the warp scheduler fetches one instruction for one particular warp. Then the codes instruction launches it onto the pipeline, register file, ALUs, maybe access to the on-chip cache or the shared memory, which is the scratchpad memory, which is also on chip. In some of the cases, the data is not in the on-chip memory, so we have a miss. We have to go to the memory long latency operation, but in the meantime, we can continue the execution of other instructions from other warps and try to hide at least as much as possible of these long latency instructions. Okay. Now we are going to go a little bit deeper, right, into how the threads and the different instruction streams, scalar instruction streams that compose, that are each of the individual threads, are executed onto the hardware when the warp is formed. Imagine that we are using 32 thread warps. Each warp has 32 threads, and it operates on 32 elements at the same time. Then, how are they executed onto the SIMD pipeline? It depends on how many of these scalar pipelines that you see here that are in parallel. It depends on how many of these we have. So in the simplest example in this slide, we have only one of them. So if our warp length for vector length or warp length or warp width is 32, this means that we need 32 cycles to go one by one and execute and start executing in this pipeline processing element or execution unit, each of the additions of one element of A, one element of E, and one element of C. In some other cases, so here we are exploiting the parallelism in time, right? So we are pipelining the execution and exploiting the parallelism in that way. We may have more than one, and actually that's the case in real GPUs. We may not have as many of these scalar lanes or vector lanes as 32. We may only have 4, but in this case we can also exploit parallelism in space, right? Because at the same time we can start computing Z0, C1, C2, and C3, and then the next ones 4, 5, 6, and 7, and so on, right? Then for each of the different lanes, we need to have a place to store these input and output operands, right? And this is the register file. We have a huge register file, typical size in one of the GPU cores in Nvidia GPUs is 256 kilobytes, which is pretty large, as you can see. What we do is partitioning this register file and assign some of the registers to each of the threads, right? And one possible way of mapping threads to vector lanes or to registers is what you have on the screen. In this case, we have partitioned the whole register file into 2 big parts, and then inside each of these parts that are connected to the lane and to the processing elements, we have the registers corresponding to thread 0, thread 4, thread 8, and here the registers corresponding to thread 1, thread 5, thread 6, and so on. And remember, I told you when the hardware creates the warp, it groups consecutive threads together, consecutive threads that have consecutive IDs, right? So 0, 1, 2, 3 are in the same warp. And because they are in the same warp, I want to execute them in parallel because I'm going to launch, or the warp scheduler is going to launch one instruction for all of them at the same time. So this is why we map them to different lanes such that they can be operated and executed in parallel. And actually we talk about lockstep execution because they go in lockstep. They go all 4 in this example, or all 32 in the general case of NVIDIA GPUs all together. And here you can see another representation of more or less the same ideas. We have a load unit, and then we have maybe some other units that execute arithmetic operations. So here, for example, in the load unit, if we have, imagine 32 threads per warp, but we only have 8 lanes, what we will do is first start the execution of the first 8, then the next 8, then the next 8 loads, and the next 8 loads, and so on, right? And by the way, one cycle later, the warp scheduler can decide to fetch one multiply instruction for warp 1 and start the execution again 8, 8, 8, 8, and then add instruction and so on for different warps. And recall the idea of vector processors and array processors at the same time. Here we have different instructions at the same time as in a vector processor, but also as in an array processor, we may have different instructions in the same unit as well. And actually that's typically what we will have for additions and multiplications, that in reality they are executed on the same SIMD lanes, and the INT32 or FP32 or FP64 units that you have previously seen in the GPU core of Nvidia A100. Okay, recall when we were talking about SIMD processors, vector processors, and we had to access memory. Recall that we needed a base address and we needed a stride, and by using these, we were able to calculate the address that we have to access from memory. Right here in GPUs, the way that we access data, the way that we address a memory to be accessed by different threads is by using the thread ID. We are not using the stride. The concept of a stride obviously exists as well, because, for example, consecutive threads can access consecutive elements in one array, so then the stride is one, but we don't have to be explicit about the stride that we are using when we program the processor, in this case, the GPU. Here, what we use is the thread ID, right? And with the thread ID, we pair one thread to one data element. This is a very simple, the simplest example that we can give is like thread 0 accesses data element 0, thread 1 accesses data element 1, thread 2 accesses data element 2, and so on. The stride, as you can see, is 1, but we don't have to use this concept of a striding our program. Rather, we use the thread ID, and you are going to see how. We need to define the number of threads that we want to use in our program. And normally, as you will see, not all the program is parallelizable. We cannot exploit data level parallelism in all parts of an algorithm or in all parts of a program. So we will still need, in our heterogeneous system, we have a CPU and a GPU, we will still need to use the GPU. For what? For the execution of serial code, or those parts of the code that maybe are parallel but have little parallelism, for example, because we want to operate on a very small matrix, 4x4 only. You're not going to use a GPU for a 4x4 matrix, right? But maybe you can use a couple of threads on your CPU, something like that. So we will have serial code in our program, and then we will have parallel code. And this parallel code is executed on GPU and executed by many threads, maybe millions of threads that we define. And the way of defining these threads is by using this kind of API where we so by using this API, we tell the hardware, we tell the GPU how many threads we want to use. And we are going to talk very soon about the syntax of this API. After executing on the GPU, maybe we have more sequential code that is executed on the CPU, and then maybe another kernel, in this case, kernel B. When we talk about kernel, what we mean is the function that executes on the GPU. So we usually talk about GPU kernels. By the way, related to the fact that you still have serial or modestly parallel sections in the code, this relates to the Amdahl's law. So don't think that you are always going to obtain amazing speedups in the end-to-end execution of your program. That will depend on how much of your code can be parallelized, and this responds to the Amdahl's law. And here you have this slide to recap on the Amdahl's law. Regarding the syntax of this kernel launch, again, we could do it in different ways, right? So maybe my program, maybe this kernel A needs 2 million threads, and I could write here 2 millions, and then the GPU could execute 2 million threads in some way. But that's not how we normally do it. The way that we normally do it from the software perspective is by grouping these threads into something that we call blocks. Observe that we are not calling them warps yet. We are calling them blocks. So from the software perspective, blocks are a number of threads, a group of threads that are somehow working together. So when we launch one kernel using this API, what we define is the number of blocks and the number of threads per block. Don't worry about this for now, because we will repeat this for sure in our next lecture, where we are going to start talking more in detail about programming the GPUs. But now you can already see that We don't declare like the total number of threads. At least this is not the case in the CUDA programming model, but we define a number of blocks and a number of threads per block. And then inside the code, inside the kernel code is what you have here. Recall that like this is, I gave you actually this example in the previous lecture. Here we have some parallelizable code, data level parallelism, this vector addition. So what we do is assigning one of each of the iterations in this CPU loop, in the CPU code, we assign them to different threads. And the way of assigning the elements, we don't have an index, and in this for loop, what we have is the thread ID. To calculate the global or the overall thread ID that is uniquely identifies one thread in the whole GPU, we need to use the block ID and the thread ID inside the block. We will talk more about this, but you can already see more or less how one of these kernel functions looks. Why blocks are used from the software perspective? Because that's also a very good way of distributing the overall computation that we need to do onto the different GPU cores. Recall the A100, it can have up to 128 GPU cores. How do we distribute the million of threads that we want to execute among all these 128 cores? What we do is mapping blocks onto the GPU cores. And then inside each of the GPU cores, or these streaming multiprocessors in NVIDIA terminology, the streaming multiprocessor or the GPU core decomposes each of these blocks that may have hundreds of threads. Typical numbers are something between 128 and 1024 threads. It divides these blocks into warps of 32 threads. And then it starts, the warp scheduler starts reading from the instruction cache, the instruction from the different warps that are going to be executed onto these different load store unit or SFUs or SPs, which are the small SIMD lanes that we saw before for integer 32, floating point 64, floating point 32, etc. So let's recap and let's start wrapping up the lecture. Again, the comparison of the traditional SIMD and the warp-based SIMD. Traditional SIMD contains a single thread. It's a sequential instruction execution. The programming model is SIMD, and the ISA, the instructions that the programmer has to write or the compiler are vector SIMD instructions. In warp-based SIMD, what we write is code for individual threads. We are not using vector instructions, we use threads. It's the hardware later that creates the warps and executes them on the hardware, on the SIMD engines that are each of the individual GPU cores that we have presented before, right? So we have an ISA that is scalar, and the SPMD programming model allows us to write code for individual threads, and then the hardware creates the warps, which are somehow the vector instructions that are executed on the SIMD pipeline. So SPMD is a programming model, not a computer organization. It gives us the possibility of executing multi-threaded programs on a SIMD machine. Each of these threads or each of these procedures in the same program operate on different pieces of data, and they can also execute different control flow paths. And as we are going to see next, it's much easier to explain. So it's much easier to deal with this control flow path divergence in GPUs than in SIMD processors. And this was the second advantage of the SIMD execution model. Recall, we already discussed this in the beginning of the lecture. We need to have a way of executing conditional operations in SIMD processors, and we had to deal with the mask, right? And something very similar as well may happen on a GPU program as well. We may have 4 threads belonging to the same warp, and each of them goes to different paths of the execution, right? How do we handle this? Well, we are going to do it in a similar way as we did using the mask for the SIMD processors, but here all of the, let's say, hard work is going to be handled by the compiler and the hardware itself. So this is an example of branch divergence. We have one warp that is executing number of some instructions here. At some point, there is one branch, again, if-else statement, for example. Some of the threads go through path A, and other threads go through path B, and then they reconverge and they continue the execution together. The thing here is that we have divergence. Not all the threads are executing together. We need a way of handling this, and what we do is using mask execution or predicated execution or conditional execution, different names for the same thing. In the end, we keep using a mask. We keep using these mask bits that determine when this thread executes, either here or here. And but this is completely transparent to the programmer. So far, the two key advantages of GPUs with respect to SIMD processors, I think that this was already like a not so quick, but quite comprehensive introduction to the architecture of the GPUs. We are going to continue talking about the architecture of the GPUs and other heterogeneous devices in later lectures. But yeah, we are almost done. Before we finish, I just want to show you very briefly how GPUs have evolved in the last 12 or a few more years from the GTX 285. There were even older generations of the first CUDA-capable generation of NVIDIA GPUs from 2006, 2007. Since then, you can see how much the number of functional units and the overall performance in terms of gigaflops has increased from this GTX 285 to the current architecture, the A100. We can see an amazing increase. The reason is that GPUs are being absolutely successful as accelerators for scientific or HPC applications, and more recently in the last, let's say, 8-10 years, also being massively used for artificial intelligence and neural networks. And this has definitely encourage GPU vendors to continue making their devices much more efficient in terms of energy consumption, in terms of performance that can be achieved, providing ways for these cores to access data at higher memory bandwidth, for example, by pairing the GPU chip with HBM memories using silicon interposers that allows these cores to enjoy much higher memory bandwidth. Yeah, we will keep discussing about this in later lectures. And also, I was mentioning neural networks and artificial intelligence. The other day, I already talked briefly about these tensor cores that are designed to accelerate deep learning and other types of machine learning workloads. They essentially perform matrix multiplication very fast. They perform dot product and multiply accumulate operations very, very fast. But in the end, if you try to find some information about them, you can, for example, read this interesting paper that where the authors have micro benchmarked the tensor cores of the Volta GPU architecture to try to figure out how this is internally built. And it seems that it's like kind of a SIMD unit where the SIMD lanes are organized into tensor cores, and these are divided into so-called octets. And there are 16 of these SIMD units in each. So there are 8 of these SIMD units in each octet. And if you take a look at the SIMD units, this is essentially a dot product on unit, right? Which is the basic operation of matrix multiplication and many machine learning workloads these days. The most, let's say, surprising thing about these cores with respect to conventional SIMD engines is that here we don't have a partition register file where each thread can only access its own registers. Here, the registers are all shared inside the same wire to make these vector product operations much more efficient. Okay. Edward, your question, I think it's good. What's the price of one of these GPUs? I would definitely recommend you to Google it. I'm pretty sure that you will find it very quickly. Okay, yeah, if you want to learn more about GPUs, for sure you can continue watching these lectures, because that's what we are going to talk about in the next lecture, for example, and a few more lectures. But if you are very impatient and actually want to go deeper into some of the things that I already presented, you can watch this lecture on graphic processing units from the spring semester. Okay, that's all from my side. That's the lecture part of today's meeting. I hope you find it useful, and yeah, feel free to ask any other questions that you may have. If there are no other questions, then we will finish with this part, and we will stop the live streaming here and continue with the discussion of the project proposals. Any other question in the YouTube chat, Resat?
I think most of the questions are answered, but if you have time to take a quick look to the last question, that would be good.
What was the last one?
Let me copy it here.
Okay.
It's a general question. I think it's good to conclude the session. Okay. Okay, I copied it here.
In the chat? Okay. Okay, yeah, this is a good question. Do we care about the complexities which the compiler and or the hardware hide for the programmer, just for fuller appreciation or for creating more performant code? Okay, so the key idea is to provide for programmers a way to easily program the architecture, to easily program the GPU, but still create high performance code. In most of the cases, as high performance as if you were directly writing the vector instructions, as if you were writing your code using a machine code. Because in most of the cases, when you program a GPU, you are going to exploit the regular data parallelism. So what the compiler and the hardware have to do is relatively straightforward, and they do it very well. You wouldn't be able to probably achieve even more performance if you write the machine code, which is not completely true, by the way. You can always achieve a little bit more performance, because if you write the machine code, for example, you can control exactly what are the registers that you're using, and this partition register file in reality is kind of a banked memory, interleaved memory as well. So there might be bank conflicts as well when accessing the register file. But normally the compiler also optimizes to deal with these bank conflicts in the register file. So as I said, if the parallelism is regular, for sure you're going to achieve, or very likely you will achieve the same performance as if you were writing like much more lower level code. Then when it comes to more irregular codes, then it's the ability of the programmer to be able to use the CUDA programming language or OpenCL programming language in a way that optimizes the code and takes more advantage of the underlying hardware. So essentially the idea is that, yes, the best thing of GPUs is that they have made much easier to program SIMD engines, but still you need to understand how the SIMD engine works underneath to be able to achieve the highest possible performance. And I think that we are going to cover in this course some good examples of how to optimize the performance, of our codes by using different programming optimization techniques. Okay, yeah, thank you very much. I think it was a very good question, same as the previous ones. It's yeah, really appreciate your attention during this lecture, and I hope you will all join our next online lecture as well. At this point, yeah, I'm going to stop the live stream. Thank you very much.